When you look at the night sky, some stars appear bright and some faint. But here is the surprising part. That brightness you see is not always their true power. A tiny star nearby can look dazzling, while a giant star far away can look like a faint dot. So astronomers used two ideas to separate illusion from reality: apparent magnitude and absolute magnitude. When astronomers talk about what is meant by a star's magnitude, they are talking about how bright it looks. But that brightness can be defined or measured in two different ways: the apparent magnitude and the absolute magnitude. Now, the apparent magnitude actually is how bright the star appears in the sky from Earth. So this is the person standing on Earth, and he would measure, or she would measure, how bright the star appears in the sky from Earth. So it depends on distance and actual brightness, which in technical term is called a luminosity. Now, say for example how bright it appears in terms of the sky from Earth. So if I say for example that the sun looks extremely bright, brighter than Sirius, but that is a viewpoint from Earth's point of view. So you can think this is an apparent observation. Now say for example if you have got Earth and Sun, and the distance is about 150 million kilometer, the sun looks blindly bright in front in our sky. Considering the other case where the Earth and Sirius is located at a distance of 81.46 trillion kilometer, which is quite far off. So the sun looks brighter not necessarily because it emits more light, but because it is much more closer. So Sirius looks bright too, though it is much farther. That means it is have got an intrinsically more powerful. From here what we can understand is that we mean that we see brightness is not always the same as what star actually gives off. So this tells actually the magnitude, absolute magnitude tells how bright the star actually is, regardless of whatever be the distance. The sun looks extremely bright because it is close to us. Sirius looks bright too, although it is much farther. That means Sirius is intrinsically more powerful. But a distant supergiant may look faint simply because it is far, far away. Now say for example if we take an theoretical case that we could place both Sun and Sirius at a same distance, which is 10 parsecs away, then we would see their true intrinsic brightness. So if we take the absolute magnitude of the Sun, which is denoted by M with a little bit of circle which denotes solar, and if I take absolute magnitude of Sirius, then what we can see is that since Sirius has a smaller and hence a brighter magnitude, it means Sirius is intrinsically brighter, much brighter than the Sun. As a matter of fact, Sirius emits, in terms of measurement, about 25 times more energy than the Sun. So the apparent brightness is not equal to actual power. Actual power is the intrinsic power, which we will see when we will deal with absolute magnitude. The sun, remember, it appears brighter, but Sirius is brighter. That means the sun appears brighter, but Sirius is brighter, and it actually reflects its internal power in terms of brightness. Now you might be wondering, well, we understand the distance because it is far off, so distance really doesn't matter. What it matters is the actual power. What is the physics? What is the law that explains all this absolute apparent magnitude and the distance and brightness? So as we see that if we consider this light bulb or any source of light, the light from a star spreads out in all directions. So as you can see, this example shows as it travels farther and farther and farther, you can see it covers a bigger area. That means it covers a bigger sphere. Compared to this, as we go further, we see it is covering a bigger sphere. That means the surface area of the spheres increases with d squared. And so the amount of energy actually gets distributed over a larger and larger area. So here is the equation which tells apparent brightness B is equal to luminosity upon 4 pi d square. This is basically what is called the equation. That means it tells that if you double the distance, let us go to the next page. So it tells that if you double the distance, brightness becomes 4 times weaker. And if you make the distance 10 times, brightness becomes 100 times weaker. So that is basically the mathematics, a simple relation between that. So if we take the sun and Sirius numerically, then we can say the sun's luminosity is this much and Sirius luminosity or distance to sun is this much. Sirius luminosity is this much and distance to Sirius is about 8.6 light years. Well, that's quite a far distance. So even though Sirius emits 25 times more light than if we consider sun, it is about 500,000 times farther away, and because brightness decreases as 1 upon d square, it took billions of times dimmer compared to that from Earth. Remember, we are talking about the apparent magnitude. So in terms of measuring apparent magnitude, what will matter is basically the apparent distance from the Earth. So this simple example actually shows that the distance to sun is about 1.5 times 10 to the power 8 kilometer, whereas distance to Sirius is about 8.6 light years. Even though Sirius emits 25 times more light, it is about 500,000 times farther away, and because of the equation of brightness with luminosity and the decrease in distance, it took billion of times dimmer from Earth, although it emits more energy compared to that of sun. So that is the reason why Sirius, though powerful, looks like a bright dot, while the sun actually floods our sky with a huge and enormous effulgence of light. Now, if I take an analogy, you can think of, imagine you're holding a candle and this candle is right in front of your eyes. As a result, it looks dazzling. Now imagine there is a bonfire which is emitting light miles away, and it emits far more energy than the candle. But from your position, the candle looks brighter because the difference lies in distance, not in the true output of light. Now, apart from these analogies and measuring the apparent brightness in terms of a simple mathematical equation, there are certain things which comes to be normal. So as you can see, this is the final line which tells difference lies in distance, not in the true light output. Now, when I'm talking of the confusion that I was talking about, that what is the confusion? So the confusion is that magnitude, if we can see as a whole, the magnitude. So whenever we talk of magnitude, we think it is bigger. It is bigger in numbers and hence it is bigger in quantity. So what we expect is that 10 means brighter than magnitude compared to that of 5. But magnitude scale comes from some ancient history, not from modern logic. So in general, we are used to think that bigger number means a bigger quantity. Now around 1500 BC, the Greek astronomer Hipparchus created a simple brightness ranking. What was that ranking? He called the brightest stars, say for example the sun, he could see is carrying what is called the first magnitude. The second one, which is a little bit slighter one, is considered to be the second magnitude. And so on until the faintest star, he numbered that with sixth magnitude. So small numbers meant brighter stars by Hipparchus' definition. Now centuries later, when astronomers began measuring light quantitatively, they actually kept what is called Hipparchus' order for tradition but refined it mathematically. This person, Norman Robert Pogson, He was an English astronomer who worked in India at the Madras Observatory. He discovered several minor planets and introduced a mathematical scale of stellar magnitudes. Now, the modern Pogson scale that actually tells a difference of 5 magnitudes corresponds to a brightness ratio of exactly 100. This is a very simple mathematical formula for the sun's apparent magnitude. Astronomers write as this. A1 magnitude makes a difference about 2.512 times difference in brightness, and this makes the scale logarithmic and not linear. So from Hipparchus' definition of the brightest star, the second, the third, and so on, Pogson's relation actually gives us a better and a more mathematical and a simple understanding of measuring the scales. So the magnitude scale runs backward, as we have seen, because it started as a ranking system. Smaller numbers mean brighter stars, and each step is about 2.5 times in brightness. Well, this is a kind of a table, a tabular structure, which gives you the magnitude and the comparison. As you can see, minus 26.7, which is the negative sign, shows in comparison a brighter star in our sky, whereas the plus 25, which is a positive number, shows distant galaxies, and for that we need telescopes. Now the question is that why do astronomers really do that? Now this is why the astronomers judges a star's power just by how bright it looks. What they do is that they first measure the apparent brightness, what we call the apparent magnitude, and then calculate the distance. And finally they derive the luminosity, the true physical energy it emits, and we will look in this further in today's video. So remember that the sun appears bright because it is nearby. So distance really matters. But many stars which are intrinsically more powerful out there, far more luminous, their distance just hides their glory. That means if they're far off, that is what is the problem. Now we come to the next important concept in astrophysics, which is called absolute magnitude. Now, so absolute magnitude is a measurement of what we are calling the star's true physical brightness. Now, when we talk of true physical brightness, it actually tells two things. Not how bright the star looks to us, but how bright the star actually is, intrinsically in terms of how much energy or output or luminosity that star is actually emitting. So the apparent magnitude m depends on distance and luminosity, and absolute magnitude m depends only and only on the intrinsic power, which is the luminosity. A simple mathematical equation shows this, where you can find out that apparent magnitude is the small m, absolute magnitude is the capital M, and the distance d is measured in parsecs. So here you can see that m actually shows how bright it appears, d is actually the distance, and the logarithmic factor corrects the brightness for distance, and capital M is how bright it really is at a standard distance. Now in the earlier analogy, what I have explained to you is that brightness decreases as it spreads out and out and out, and this is given by 1 upon d square. Why? Because light spreads over larger area. Now the magnitude scale is logarithmic, so the inverse square law, which you can see, it turns into the distance modulus formula, which I have explained earlier. Now because light spreads over a larger and larger area, the magnitude scale is logarithmic. So you can truly compare which bulb is powerful, which candle is weak, and which torch emits more light. If you imagine every light, for example a torch, a candle, or a bulb, is placed at a distance of 10 meters on the table from you. So we take the same analogy which we did with apparent magnitude, and we place, for example, Sun and Sirius at a distance of 10 parsecs away. And if we do a simple mathematical calculation taking sun's apparent magnitude and sun's actual distance in terms of parsecs, then with the absolute magnitude formula we can plug in the sun's number. We can do this computation in terms of logarithm, and what we get from here is this. Approximately plus 4.83, which is the absolute magnitude of the sun. So what it tells is that if the sun, for example, were moved at a distance 10 parsecs, it would look a faint star of magnitude plus 4.83, just barely visible to the naked eye. This is an example of calculating the absolute magnitude of sun, and remember we have put both those, sun and Sirius, at a distance of 10 parsecs so that the mathematical calculation carries a kind of a parity. If I do the same kind of an example with Sirius, then we know Sirius' apparent magnitude, we know the distance using the same formula. We can further calculate the logarithm, and what we get is around plus 1.42. So if Sirius was placed at a distance of 10 parsecs, it would look like a magnitude plus 1.42 star, bright and clearly visible. Now from here you might have a question that what is this? I mean to say what this comparison actually shows. The comparison shows that sun looks incredibly bright because it is extremely close, and Sirius looks bright because it is intrinsically powerful. What it also shows that sun with a 4.83 magnitude, luminosity is faint, whereas plus 1.42, which is lesser than sun, it looks much brighter. So what it tells is that their true power, when we move both the sun and Sirius at a distance of 10 parsecs, the sun becomes a faint plus 4.83 star, but Sirius remains a much brighter with just plus 1.42 star. So this is the power of absolute magnitude. It strips away distance and it reveals the star's true luminosity. So from here what we can further say is that absolute magnitude it tells us not how bright the star looks to us, but how bright the star actually is. Now I have been talking about the factor that it is the actual output which is technically called luminosity. I would like to show you what is the relation it has with luminosity. So technically we can say that luminosity actually means how much energy the star emits per second. So obviously this is an intrinsic property and it does not depend on the distance. So if I take the absolute magnitude, it's designed to exactly like this, which we have already seen. This is a new equation and it tells that M1 and M2 are the absolute magnitude of two stars, L1 and L2 are the two luminosities, and a difference of one magnitude, say for example 2.512 times difference in luminosity, and a difference of 5 magnitude means 100 times difference in terms of luminosity. So we are just multiplying that factor. Now astronomers usually, because 2.512 squared is equal to 100. Now astronomers generally use the sun as a reference for a kind of a standard, and often astronomers and we compare that to a sun. So the relation becomes this, and if we rearrange, the equation looks like this. Now it is a fairly straightforward algebra, nothing deep or difficult mathematics, but I would like to show you this example comparing that with a Sirius and sun. Now the star Sirius, we know what is their values, we have just calculated that. So here if we go further, we can get the difference if we minus as 3.41. If we plug that into the luminosity formula, we get something like this. What does it tell? It tells that Sirius is about 23 times more luminous than the sun. So this calculation actually proves the fact that internal energy or luminosity of Sirius is 23.1 times more than that of sun. And it actually more or less matches with the astrophysical data, which is about 25L. Now here I would say M means the absolute magnitude of a star. If this so a bigger luminosity means the star emits more energy, and a fainter luminosity means emits less energy, hence larger or dimmer absolute magnitude. So here you can see if M goes down, L goes up, and if M goes up, L goes down. It's very simple, nothing to worry about this. So absolute magnitude, what it tells is just a different way of writing luminosity, but it tells you how powerful a star is, and output is on a logarithmic brightness scale. Now absolute magnitude of the sun is basically if the sun were placed at a distance of 10 parsecs away from Earth. But remember, it should not be confused with the apparent magnitude of the sun, because apparent magnitude tells how bright the sun actually appears to us. That means from Earth, from its real distance, which is around 1 AU or astronomical unit. So this is all about what is called apparent and absolute magnitude. The next concept in today's video which we would look, which is very, very important and interesting, is what is called a Roche Limit and a Roche Lobe. Now it is a kind of a French pronunciation, which in Switzerland people pronounce it as Roche. But well, that might sound a little bit odd, so we will stick to the English pronunciation, which is called a Roche Limit. Now, when we are talking of Roche Limit, for example, we are actually dealing with something which are called gravity and tidal forces, and all this actually stems from one question: what happens to a smaller object when a massive object or a massive astronomical object pulls on it? Now this is actually the basic of our discussion. So a smaller object when a massive object is pulling around. Now this was actually found first by, so the Roche limit is the minimum distance at which a smaller body can orbit without being ripped apart. That means if it crosses the limit, it will be torn apart. Now it was first propounded by Edouard Albert de Roche, who was a French astronomer and mathematician, and he is best known for his work in the field of celestial mechanics. His name was given to certain concepts like Roche sphere, Roche limit, and Roche Lobe, the last two which we would be dealing in today's video. Now imagine a moon which is slowly spiraling towards the planet. So the moon is far away, the planet pulls on it, but the force is nearly equal across the moon, so everything is fine. The moon remains perfectly intact, no problem, and the moon's own gravity, for example, like a glue stick, keeps it together, rotating around. Now what happens as the moon gets closer and closer, and there are tidal forces which are increasing. Now in order to explain that, we need to divide this sun and moon orbiting in a kind of a phase, and which I'm going to do in the next part of the video. Now on your right hand side is Earth, and we have got a moon which is circling around. I cannot show the animation right now, so you have to just extend your mind and think that this one is moving around. So the first phase is one where obviously the moon orbits in the planet safely, the distances are fine, and there is no anomalies which are happening. Now say for example here at phase 2, what we can see is the moon gets closer, the tidal force increases. And as the planet's gravity is stronger, because on the near side it is coming closer, there is a tiny stretching. So you can see from figure 1 to figure 2, the figure 2 is a little bit elongated. So it becomes elongated like a football. Now if it further goes near, so point number 3, at phase 3, we see that the moon is approaching the Roche limit. So the difference in gravitational pull across becomes significant, tidal forces grow rapidly, and the equation is reversed. So it will be 1 upon d square, which we have seen earlier, and the moon actually begins to feel the stress. So you see more than the figure 2, figure 3 is a little bit stretched. It might also happen that internally the part which is facing the Earth, there are cracks which are forming. And then we come to phase 4, and here it is reaching the Roche limit. That means tidal stretching is equals to moon's own gravity. The moon now cannot hold it together. That means there is an anomaly, there is a disturbance, there is an imbalance which is striking. So from figure 3, as we move to figure 4, you see that it is stretched a little bit more. And here comes the final phase, that it has crossed the Roche limit, it is fragmented and it is broken apart in small parts, and outer layers begin to stretch, blocks of materials lift away, and the moon slowly starts to disintegrate and starts breaking in small parts. Now I have omitted the later phases, and I have summarized that in this. Some of the pieces will fly away, they will form a kind of a ring system, the debris will spread out, and the moon is shredded into countless small pieces and fragments. And as you can see, this is basically a standard table which tells you about the Roche limit of rigid and fluid. I will come to that later. But what is the Roche limit of a moon, Earth and Jupiter? That means how much it will stay, and after that how it will start to disintegrate and break down. Now all of this burns to one single concept, that why is coming too close is the key. That means all these things are coming close to each other. Why it happens? So here you can see, if I take the Earth and the moon, the gravity drops with distance. So this part, the yellow part which you can see, this is near side, which feels much stronger gravitational pull. Whereas on the other hand, this part which is far side feels much weaker pull. Why? Because it is far away from the Earth, and hence it experiences less gravitational pull. So the difference becomes violent. The object gets cracked, and the object gets stretched and cracked and shredded. So all in all, what we can say is, if the body crosses the Roche limit, then when it gets so close to the planet that the planet's tidal force becomes stronger than the body's own gravity that could hold together. Now there is a very interesting question which might be creeping in your mind, is that is the Roche limit we talk is just I would say applicable only to moon? Is it something which is applicable to moon? The answer is a big no. The Roche limit is something which is I would say it is universal. It is applicable everywhere. So it applies here, as you can see, any body which is orbiting any other, provided few conditions. One is that one body is massive. For example, a planet, it can be a big star, it can be a black hole, and the other body is held together by its own gravity. For example, a moon, an asteroid, a comet, or it could be a dwarf planet. So the answer to this is Roche limit is universal. It applies to anybody provided you maintain these two conditions. That means one body is massive and the other is held together by its own gravity. So Roche limit is applicable to moons around planets, comets passing planets, stars orbiting black holes, exoplanets, and even asteroids, because they are passing too close to planets. So from here what we can say is that here you can see that if it is the moon and the Earth case, then this is the orbiting smaller body and this is basically the central body. So Roche limit depends on both of the bodies. So anything which is why it is limiting on both bodies, the reason is that tidal forces depends on these two factors. The mass of the central body, say for example the Earth, and the density and structure of the satellite, which is the moon. So anything which is held together by gravity can be torn apart, can be disintegrated, can be broken apart by tidal forces if it gets too close to a larger body, and Roche limit is actually a measure of that. Now, as I talk about Roche limit, and you have seen in this video that there are two things which are coming. One is called Roche limit for a fluid body, another is called a Roche limit for a rigid body. Well, what does it actually comes to play? What does it mean? So remember that there is a wrong notion. In astrophysics, fluid does not mean like a water which is flowing. It actually means that object which is held together weakly, I mean to say just like fluid, that tidal forces can break or deform these parts. So it is not water, but something like water which is held very weakly. So when we talk of a fluid satellite, it can mean its internal strength, it can mean gravity is the main thing holding, it can squash or deform or under tidal forces. So you can see of example of fluid bodies can be comets, icy moons, gas moons, long loosely bound asteroids, and so on. So these objects, you need to understand, are behave like gravitationally held blobs. That means they are not like solid rocks. So the word comes fluid. That means which is not water. It is something water-like, not strongly held. Now when we talk of Roche limit for a rigid body, we meant to say it is a rigid satellite. That means those materials or internal structure has a structural strength, and it can resist. It can actually hold itself together before being stretched or torn. So rigid satellite means rock, things which has got strength, and tidal force needs to be very, very strong in order to disrupt their equilibrium. So examples can be rocky moons like Earth's moons, iron nickel asteroids. It can be solid rocky bodies like Mars-like, Mercury-like objects, and many other. So all in all, rigid body means they do not deform easily, so they survive closer to the planet. Now there is a mathematical equation, very simple, which I'm not going to explain or take mathematics in that. This is the Roche limit for fluid body. This is the Roche limit for rigid body. And these indices actually means that you can pause and have a look at this if you are really interested. So this table actually shows you what is the satellite type, what is their strength, what is their behavior. That means do they easily deform or it holds, and what is the formula that you would use. For slow weak bodies you use the fluid body Roche limit, and for rocky moon or metal you use what is called the Roche limit for a rigid body. So if the object is squishy, simple, you use the fluid Roche limit. If the object is stiff, then you can use the rigid Roche limit. It can survive much, much closer. Now, before we go ahead and understand the next and the final concept in our video, which is called a Roche Lobe, first we need to understand a very simple concept which is called a binary star. Now, a binary star is something looks like this. What it is telling is that there is a star system where two stars orbit around a common center. Now this is very important, and each of them are pulling on the other through gravity. So here you can see the yellow one is pulling the white one and the white one is pulling blue one, and they are orbiting around a common center of mass. So most important is that they are not one star going around the other, but they actually orbit around a shared point, a common point, which is technically called a barycenter. So here you can see this plus red one is the barycenter. So barycenter, you can understand that it is basically a common balance point. For example, if two people are sitting on a seesaw, then the barycenter is the point where the seesaw balances. So here you can see that the two objects going around the barycenter, the red cross, which objects orbit each other. So in space, planets and stars orbit out this balance point, not each other directly. So for example, Earth and Moon both orbit on their barycenter, which lies just under the Earth's surface. So from this we can understand the concept of a binary star which are orbiting around. They are orbiting around a common center which is called a barycenter, which balances these two. And from here we get a few important things. First is that there are two big gravitational pulls. That means both stars are quite massive, quite big enough to strongly pull on each other at a surrounding space. They actually share a common orbit, which I have already explained, the barycenter. And there is a gravitational kind of a tug war. That means each star is trying to hold on nearby matter by creating a competition that defines what are their gravitational boundaries. So this one, the white one is going around trying to create a matter. The blue one is going around and trying to create a matter. So when we talk of binary stars, these two stars orbiting around, we get a figure like this. So here you can see this this one, the left one lobe, is basically has a bigger star. It is a bigger star. So the Roche Lobe is bigger because its gravity is stronger. And this one on the right hand side, this is small. So obviously this has got a Roche Lobe which is less. And this one, L1, is basically called the Lagrangian point. Okay, in order to do that, let us quickly turn on the page and explain things a little bit better. So what we have understood is that Roche Lobe is basically a gravitational territory, a place around a star in a binary star system where inside which material belongs to that star. So we take our diagram once more and we try to explain this concept clearly. So first of all, we will start with the left one. So the big star has a bigger Roche Lobe because its gravity is stronger, and a more massive star has a stronger gravity, obviously, which creates a large gravitational bubble and therefore a larger lobe. Now this point which I'm trying to point, L1, this is a sharp point where the two lobes, you can see they're touching each other. This is what is called the Lagrangian point. It is the balance point in this gravitational tug of war where the left one is trying to pull the right one. So L1 is the place where the gravity of both stars is exactly equal, and there's a lot of matter sitting here and it does not know which star this matter belongs to. So this is the reason Roche Lobe overflow happens, which I will explain to you later. Now on the right hand side here you can see the right lobe is smaller. And this smaller is because the larger star on the left has expanded or gone beyond the L1 point, and it fills the whole lobe. Its outer layers are no longer gravitation is secure. That means it starts to create form. Here you can see this is the yellow one is what is the matter. So what we can say, if it goes a little bit further, that means the material will flow through the L1 point onto the small point. So here the material will start and it will go to the smaller one. So that is very important. So what this diagram actually shows is a star so large that it nearly fills its Roche Lobe. And these teardrop kind of a shape are basically the Roche Lobes, the gravitational bubbles which forms around each star, and the larger the lobe, the left one lobe belongs to the massive star and the small lobe belongs to the lighter star. So if the large star expands to this point, the gas will start flowing from one star to another. Here is a better diagram which will explain to you now the process. So this is a diagram which depicts a binary system. So first I will start with this, which is the companion star. What do we mean by a companion star? This is a normal star, just a normal star which is orbiting the compact object. This is distorted, as you can see, due to the extreme gravity of the compact object. The stretched shape of this star shows that it is closing to filling the Roche Lobe, meaning that matter can escape from it. Next we come to this part which is called the X-ray heating. The side of the star facing the accretion disk receives the highest intensive X-rays. So the X-rays hits the star surface, it heats up, it glows more bright in the optical UV. Third we come to this one, which is very simple. This is the star, a side of the star which is facing the accretion disk. You can see the accretion disk forming just below, and it receives intensive X-rays, and X-rays hits the star surface, and from here though the star it starts flowing into the Lagrangian point L1. Then we come to the outer accretion disk. This disk is cooler at a larger radii, so it emits optical light and ultraviolet rays, so the viscous forces spreads across the disk. Then we come to the next one, which is called the inner accretion. Here near the compact object, the disk becomes extremely hot, so million kelvins temperatures, even hotter corona. And this region, it sits outside what is called the innermost stable circular orbit, ISCO, for a black hole, which I have not mentioned over here. And finally we come to this jet radio IR part, and this is highly collimated jets, shoots out perpendicular to the disk, and it is powered by magnetic fields and rotation, emits mostly radio and infrared due to synchrotron radiation. So this is actually what it tells you, the process, the binary star process, the companion, the jet accretion disk, the jet flow, and how it goes ahead. Now you might have a question that everything is fine, so do we have a mathematical formula to calculate the Roche Lobe? Now here is a problem, and now the problem is that in terms of when we are talking of calculating the binary, the Roche Lobe limit, it actually has something which is called a three-body problem, three-body gravitational potential. Now what do I mean by that? Now you see here there are two stars pull on the gas. So first is this star, the bigger one, which has got a bigger Roche Lobe. Then the second one, which has got a smaller Roche Lobe. So two stars pull on the gas, and the rotating system adds a third term, which is called the centrifugal potential. So first we have the bigger Roche Lobe, the bigger star. Then we have the smaller star, that is the second. And then a third term, which is called the centrifugal potential. Now taking the first, second and third, because there are two stars, we have got two gravities plus rotation, there are new behaviors which emerge and which makes things a little bit difficult. That means that Lagrangian points appear, L1, L2, L3, etc. And these special equilibrium points do not exist in a pure two-body world. So that is point number one. So I mean to say, what are the problems we encounter in order to calculate a Roche Lobe, and why we do not have a straightforward formula? So first is that we have got a three-body problem, the first star, the second star, and the centrifugal potential. Then we see because of this we get Lagrangian points L1, L2 and L3, which is not present in a two-body problem, because L1 is the famous bridge between the Roche Lobes. Then we see what are that the Roche Lobes appear. Roche Lobes are basically contours of three-body potential. So if you do not use the three-body effective potential, then you cannot draw Roche Lobes, you cannot find where mass transfer happens, a lot of problems. So mass transfers cannot be explained. So the Roche Lobe is not spherical. So first thing is that it is a teardrop kind of a shape. So in order to compute a straightforward formula, we need to solve what is called the three-body gravitational potential. Now, in order to do that, in order to solve this complex potential, so astrophysicists and astronomers have found out a more or less approximate, but this approximation is almost, I would say, extremely accurate. So this is what is called the Eggleton's formula, where you can see this RL1 is basically the Roche Lobe of radius of star 1, and A is nothing but the separation between two stars. So this formula, what it tells is that it gives the radius of a sphere whose volume equals to the Roche Lobe, and that makes things easier. How? For example, if you have RL1 and you compare it with the actual radius of the star. So if R, that means the radius of the star, is less than RL1, you say the star is sitting comfortably inside its Roche Lobe, no problem. If R is equals to RL1, then the star touches its Roche Lobe. That means what? That means mass will start flowing in, so the mass flow happens. And if the R is greater than RL1, obviously the star overflows and the accretion disks form around the companion. So this is a kind of a very smart, clear, approximate but an accurate way of calculating the Roche Lobe, the limit where the mass flow happens. So here is another diagram. Here you can see first one is the donor star, and all those red lines which I just highlighted, this is where the mass flow starts, and this is basically the accretor star. So the Roche Lobe actually is a radius which tells when the mass transfer begins, and this Eggleton's formula, which we just plugged in, is a mathematical formula, and what it defines a star Roche Lobe, that is the size of the star's Roche Lobe, and this decides when and how the mass transfer will begin in a binary system. So that is the reason I first gave you the example of a binary system, binary star. Then we saw something which is called a barycenter, and from there the concept of Roche Lobe emits, and the Eggleton's formula is a nice approximate but yet a sophisticated way in which these three phases actually tells you how, where and when the mass transfer and the star overflow will begin. So that is all for today's video. Thank you very much for watching those. If you have really liked this video, please do not forget to subscribe to my channel Physics for Students and keep this bell ringing, because there are a lot of surprises and new videos coming up which this bell icon will keep you ringing. Follow me on my Facebook, LinkedIn and other social media channels, and you can write to me at this email ID. Physics for Students will be soon back with a lot of other videos. See you soon in the next video, but till then, may the good Lord be with you.